topic of proof tactics, as Olivier Kieser is going to talk about the second version of Mtac.
Thank you. Hi, I'm very excited to talk about Mtac2 and type tactics for backward reasoning, which we think is a very promising approach to proof automation in Coq. But before I get there, let's zoom out a bit. So in the last 10 years or so, our field has produced a large array of frameworks to perform large-scale machine check verification of programs, data structures, libraries, and so on. Robert also mentioned some of these: Bedrock, VST, DSpec, FTSL, and Iris in particular, which was mentioned in the previous talk. And one key aspect to all these frameworks is proof automation. We want to automate the tedious and boring parts of our proofs. And in particular, for the projects that are listed here, which are all implemented using the Coq proof assistant, proof automation means Ltac. Ltac is Coq's built-in tactic language. And the problem with Ltac is that it's a terrible language. As one Coq developer, Pierre-Marie Pedro, puts it, Ltac, the PHP of proof assistants. And it's an apt comparison because they both started out as sort of small languages meant to solve a particular problem, and then they grew into this mess of features that all have corner cases and interact in subtle ways. And we claim we can do better than that. Before I get there, let's look at the troubles with Ltac. In particular, let's look at an example of real-world Ltac code, which in this case was actually taken from Iris proof mode. Okay, Robert also already mentioned this. Just quickly, Iris is a framework for separation logics, and it comes with its own proof mode, and you saw an example of this before. So here again, on the left, you have a proof script in the Iris proof mode. On the right, you have a goal and separation logic. And in this particular example, the goal states that we assume ownership of a location in memory, X, that currently has value 8. And under that assumption, we are conducting a proof of safety using this weakest pre-assertion here of this particular let expression. And in particular here, if we execute this expression, we're claiming that it will return value 16, and it will leave the location X unchanged in memory. Okay, so then we can introduce this assumption using the IIntros tactic, and as you've seen, this will now be moved into the spatial context, the context for separation logic assumptions in Iris proof mode. And then we get to a more interesting tactic for us. And this tactic is called WP pure. And what WP pure does is it allows us to perform pure steps of reduction in our expression here. And in particular, what we're interested in is reducing this division that we have in our let expression, 8 divided by 2. And we specify that using this slightly more general pattern, anything divided by anything else, which in general you can leave out. I'm just putting it here to be extra explicit about it. And so when we execute that tactic, what it really does is it applies a lemma. And in particular, it applies a lemma backwards, which means that here we have this lemma WP pure. And what this lemma in particular states is that if we want to prove safety of any expression E1 in an evaluation context K, then if that expression E1 reduces to another expression E2, we can instead prove safety of E2 in the context K. So what WP pure will do is it will take that lemma, try to apply it to the goal, so we'll have to match up these two things here, the conclusion and the goal, and then when we execute it, it will perform the step of reduction, which in general can come with a side condition, right? We're reducing a division here, so we should better prove that 2 is unequal to 0. In this case, the tactic takes care of that for us, and we're left with the safety proof for the reduced expression. That's nice, and then we can continue with our proof. So WP pure is an instance of a backward reasoning tactic, and that means any tactic that starts from the goal and works backwards by manipulating the interactive proof state, introducing new goals, transforming the goal, or solving the goal. Okay, and WP pure is going to be our running example, so let's look at the implementation. Here's the code for WP pure, and I'm going to walk through this very quickly. So the most important aspect is that the first thing WP pure does, it matches on the goal, right? And it looks for, in particular for goal in Iris proof mode, and specifically for proof of weakest pre for some expression E. And then when it finds such a goal, it calls a helper tactic. And this helper tactic is called reshapeexpr. And its job is to take the expression that we've seen, previously that let expression, and decompose it into evaluation contexts and redexes. Evaluation context K here in yellow and redexes E prime in green. And what it will do is it will iteratively go through these decomposition candidates and feed them to the callback that we provide to it. And reshapeexpr will stop as soon as the callback succeeds with the given decomposition. And in our case, this callback first tries to unify the reduction candidate, the redex E prime, with the pattern that we specified. And as you remember in the previous slide, we said that we're looking for a division. And that's what this unify command here does. And if that succeeds, we apply the lemma that I've showed to you. And we handle the subgoals using different tactics, and we'll get back to these later in the talk. Okay, so I promised you to show you the issues with Ltac code, so let's see what the problems are in code like this. So the first thing that could potentially arise in a tactic like WP pure is a goal lemma mismatch. So I told you we are matching on the shape of the goal, and we're applying a lemma, and we better make sure that these two things match up, right? That the conclusion of the lemma should match the goal that we found. But in general, Ltac does not ensure that. So if we apply some completely unrelated lemma here, Ltac will first accept that at definition time and then later complain at runtime about the mismatch. And similarly, even if we apply the correct lemma, we may still get the arguments wrong. So for example, here I've mixed the order of the arguments up a bit. And again, Ltac will happily accept that and then later complain at runtime that we've messed this up. And similarly, all these follow-up tactics that we assign to the various subgoals from applying the lemma, they should match the types of these hypotheses, right? And again, Ltac does nothing to help us here. If we, write different tactics or mess up the order, Ltac will accept this and only complain at runtime. And to make matters even worse, in this particular tactic, we have this backtracking mechanism, right, to try the next candidate for the decomposition. And this backtracking should only happen in two very specific failure cases, but Ltac does not give us a way of specifying that, which means that the tactic always backtracks, even when the error is not one of these particular failure cases here. So in any failure means backtracking. It means we can't even write the tactic the way we would like to write it. So even with shortcode like this, we've already identified 4 potential issues. And if you look in particular at the first 3 ones, they're all related to type mismatches, right? So what this really calls out for is a type system. Ltac needs types. And there's been quite a lot of work on approaching this problem. And the most promising one for us is that of Mtac. Mtac was introduced at ICFP 5 years ago by Beda Ziliani. And they had the great idea of reusing Coq's own term language to write tactics and Coq's rich dependent type system to specify tactics. And of course, Coq's type system doesn't allow for effects that you need for tactics, such as unification, creating meta-variables, unbounded recursion, exceptions, and so on. So they added a monadic type, written capital M of T, to type these tactics. And then they have a run primitive to execute these monadic tactics. The issue, however, is that Mtac had no interaction with Coq's proof state. So it couldn't spawn new subgoals, couldn't transform goals, and it also didn't have proper backtracking. So these two things taken together mean that we couldn't have written a tactic such as WP pure using Mtac. And that's exactly what we set out to fix. So we want to fulfill Mtac's original promise of type tactics in Coq by extending it with support for type backward reasoning. And this is exactly what we did in Mtac2. Mtac2 is the first tactic language to support type backward reasoning in Coq. And the key contribution of Mtac2 is to define yet another monad that extends Mtac's monad M with backward reasoning. And on the implementation side, we've of course had to teach Coq how to integrate these tactics with its own proof state. We had to implement backtracking, in this case using the exceptions that Mtac already had. And then we've taken this WP pure example that I've shown you earlier and ported that to Mtac2 without really changing anything else in the Iris proof mode development. Okay, let's look at a side-by-side comparison of the Ltac version of WPPU and the Mtac version. So superficially, they look kind of similar. You see that the Mtac2 version has a bit more noise in it, and of course some of that is due to the tracking of types and so on. But actually a large part of it is because we now have proper error handling, and we can write the tactic in exactly the way we want, such that it only backtracks in these two particular failure cases. And that accounts for most of the difference, actually. And then there's another sort of visible difference, which is that the Mtac2 version doesn't really match on the goal. Instead, it specifies exactly in its type the shape of goals it can be applied to. And that's done using this ttac type you see up there on the right. And we'll get back to that in a second. But first, let's see how the Mtac version solves all the issues that we identified with the Ltac version. So let's look at the mismatch of lemma and goals, right? The goal-lemma mismatch. So since we now have type tactics, and the shape of the goal is documented in the type of the tactic here, and all of this is type checked by Coq, right? We're using Coq's type system. There really isn't any potential for a mismatch here. If we were to apply a completely unrelated lemma here, Coq would immediately complain that this makes no sense at all. Similarly, just the tactic, this apply primitive here, this is already checked by itself, right? As is every term in Coq. So if we mess up the arguments there, or we leave out some arguments, then Coq again will simply complain to us. And also the issue of sub-goals and follow-up tactics being mismatched is also taken care of, because all the sub-goals that are spawned by applying this lemma are again matched with type tactics. And any mismatch there will yet again lead to a type checking error. And finally, oh yeah, again, so if you mess something here up here, then Coq will complain. And finally, I've already mentioned that we have modular error handling. We use exceptions from Mtac, we inherit them, and they let us write the tactic in exactly the way we want to write it. Okay, so the Mtac2 solves the issues that we identified with Ltac completely. These are all gone now. And our secret source is this ttac type that I talked about, right? And there's one obvious question that comes up, which is, why wasn't the monad from M good enough to do this already, right? It was already typed and so on. So let's consider for a second that we simply were to define ttac of P to be M of P, right? Then if we run a tactic, there are two possible outcomes, right? The first one is a total success, right? We produce a proof of P. And the second one is failure, right? We throw an exception. However, this is not enough for WP pure. Let's see why. So I haven't talked about this in detail before, but the sub-goals that are spawned by applying this lem WP pure lemma in WP pure, they are not as necessarily close. So in particular, there was this side condition for the pure reduction that we're doing. Let's say, you know, the denominator of a division has to be unequal to 0. That side condition is solved on a best effort basis, right? It may or may not be close, and the success of WP pure should not depend on whether or not that goal is close. And what that means in terms of the proof term is that the proof term has holes in it, and these holes correspond to sub-goals that follow-up tactics can then solve, or that are then given to the user to solve. Okay, so what we get from this is that we need a slightly different semantics for these tactics, right? So we still have the case where the tactic completely fails with an exception, but we also have the case where the tactic succeeds, but the resulting proof term may have holes in it, right? And these holes we want to track as spawned sub-goals. So we need a way of accounting for these dynamically spawned sub-goals in the type of type tactics. And that's exactly what we do, right? So our final definition of type tactics is not much more complicated than what we had initially. We simply add, in the success case, we add a list of spawned sub-goals to this type here. And we call this proposition P here the static goal because it's documented statically in the types, and these other goals are the dynamic goals. Now, I haven't talked about this type goal here, right? And that's very interesting. So intuitively, a goal is really just a meta variable, right? A unification variable, or EVAR, as it's called often. And that's indeed part of the story. However, in practice, this goal type needs to account for changes in Coq's proof context that happen during the execution of a tactic. So the actual type is a bit more complicated. Sadly, I won't have time to get into that, but please look into the paper for an explanation of these additional constructors here. Okay, so now we have this very simple definition of ttac. Let's see how we can define all these combinators that we needed for the Mtac2 version of this WP pure tactic, how we can define them using this type, right? In Coq, by the way, I should say. So the first one is a combinator you haven't seen. It's called defer, and it simply gives up on the static subgoal. It converts the static subgoal into the dynamic one. And the implementation is correspondingly is very easy. We call Mtacs primitive to create a new existential variable and return this, which is now just a hole, as our proof term. And then, of course, we need to account for this new dynamic subgoal by simply wrapping this hole in this one constructor of the goal type and returning the singleton list of dynamically spawned goals. We're using defer for the try combinator, right? So the try combinator takes a tactic, a type tactic, and it executes that tactic. And if anything goes wrong there, we simply defer the goal, right? So we're still successful, but the static goal is now turned into a dynamic goal. Now, more interestingly, let's look at apply, right? So apply takes a proof of some proposition P and claims to produce a type tactic of type P. And the implementation couldn't be simpler. We already have a proof, right? So we simply return that, and since we haven't deferred anything, the list of dynamically spawned subgoals is empty. And now, of course, you may wonder what happens if we don't already have a proof of P, but we have some implication, right? We have a lemma that takes some hypotheses. So for that, we go to the chaining operator. And the chaining operator takes a tactic that produces an implication from P to Q and a proof of P. And again, the implementation is sort of straightforward. We execute the first tactic to get the implication, lowercase f here, and then we execute the second tactic to get a proof of P. And now we can simply apply f to this proof of P, x here, and arrive at a proof of Q, which is what we wanted. And we should, of course, also account for all the dynamically spawned subgoals during the execution of these two tactics. And so we collect them up and return them too. And some of you may have noticed that these two things form an applicative functor. This simple definition of type tactics means that we can define all these things in Coq. And that's really the takeaway of this particular slide here. So there are many things in the paper that I haven't had time to talk about. In particular, there are detailed introductions to Mtac1 and Mtac2. We have the full explanation of the goal type. And there's also an explanation of how to write dynamically typed tactics a la Ltac. So when you don't want to account for all the types, we can do that too. And of course, the case study from the iris proof mode in all its gory details, including full explanations of how WPPO really works, and also the now dependently typed helper function reshape expert that I'm very happy about. Okay, so to sum up, type backward reasoning with Mtac is easy. It's scalable. It's ready to be used by all of you. And you can find Mtac2 at this GitHub URL, or you can also find it in OPAM, and I'm happy to take questions. Thank you.
So a first question by Boyot said, what does Mtac2, how does Mtac2 compare with elaborator reflection in Idris? And Idris tactics written in Idris.
I don't have a good answer to that, I think, because I'm not so familiar with laboratory reflection. Yeah, I'm happy to take this offline. Please come talk to me afterwards.
Okay, Jesper asks, how hard is it to convert existing Ltac tactics to Mtac2? And if there are any examples for which this conversion is just impossible?
Oh, well, of course, if your tactic does something very general, it might be hard to give it an interesting type. You can still give it a type. It might just not be very informative. Generally, converting from, let's say, Ltac to Mtac2 is, well, as hard as going from a dynamically typed language to a statically typed language. In our example, it was not particularly hard. There were some intricacies about how to type these helper tactics and so on. But if you're already familiar with Cox type system, it should not be a huge challenge. Although this may totally depend on your particular tactics.
Thank you. So Joy asks, how well can Mtac interact with Cox built-in automation tactics that need type information, like construct on hypothesis and exists?
Interact with them. I mean, we can always call Ltac tactics, and they basically just work. If that's the question, then that would be the answer. Apart from that, we also have our own versions of some of these tactics. Yeah, okay. Again, if that's not the question, please come talk to me afterwards.
Okay, so last one, I guess it's answered there, but Anonymous asks, when can we use Mtac2?
Now, and please use it. Send us bug reports. I mean, there are going to be bugs somewhere, I'm sure. Yeah, tell us about your experience, typing your tactics.
Thank you very much.
Thank you.